Hey, how y'all doing?
Good.
Two thumbs up. Okay, cool. Um, Maybe we'll just do the regular thing for an hour and we'll be good for the day. Hopefully the video is clear at your end. I've noticed on my computer it's a little on the glitchy side. If you let me know there's a problem, I would appreciate that. Okay, so sharing screen. Boom, go. Okay, so just to make sure we're all on the same page, it's Wednesday, which means we're partway through the time window when you could be taking the midterm exam. The midterm exam, again, if you haven't, maybe some of you are finished, but for those of you who aren't, the midterm covers through chapters 1 and 2. Yesterday we said, okay, we're gonna make it live. Today we're in new content. Only chapters 1 and 2, material from the first 5 class sessions, is related to your test. So last time we talked about chapter 3, section 1 and 2, scatter plots and correlation. We're going to be moving further forward today, and I hope to get through all of 3, but if not, you know what? Some of it is for Thursday, and that's okay too. Want to shut that down. Also, before we turn you loose for the lab, remind me that I want to sort of show you one thing about the lab activity. Okay. Um, while I'm clicking my way into week 2, part C and D, Wednesday, Thursday of week 2. Want to mention I really appreciate one of you volunteering to switch sections because there was a group for whatever reason that became of size 2, and now they are back up to 3. And that guess means that one of you had a group of 4. Actually, 4 of you had a group of 4, and now 3 of you are in a group of 3 that used to be in a group of 4. Actually, hold on, all 4 of you are. But yeah, I swapped a person from group of 4 to a group 2, and you know you're involved if you were the person who was swapped, and we should be good moving forward. Again, probably tomorrow I'm going to sort of send out yet another survey of like, hey, how this week's lab groups work out. Hopefully, most of you are at least as happy as before. If you are less happy than in the first week, you need to let me know that information, and there may be a way to get it perfectly resolved, but yeah, it's always the thing. Okay. Um, so with that in mind, let's talk about office hours this week and Thursday in particular. Thursday will be the normal morning hours, but normally Thursday we would have office hours following class at like 5:10 till 5:35. It's going to have to be again before class on Thursday. Okay. And there's always the opportunity to sort of let me know, hey, that won't work for me. I need a this time or that time, and we'll figure it out. Okay. So I think I've said all the things related to administrative details that I wanted to mention. Do any of you have administrative questions? How about questions related to the look and feel of the exam? And again, if you've already started the exam, yeah, don't phrase your question in such a way that other people get information about the content. That's strictly illegal according to the syllabus. And so, yeah, just don't be that guy. Any questions about the look and feel of the test? Okay. Any questions about content from yesterday and the correlation coefficient in particular? Okay, so what I want to do is to back out of there over on this window and just, excuse me, note that the method we're talking about today in class in chapter 3, section 3, Literally, we could have a full-on class about that. Actually, we do. It's called, well, in quarter speak, Stat 324, or 334. Heck, we have other names, but this thing called regression, okay, and sometimes it's called least squares. Super important. And so what I'd like to do is to sort of tell you two stories to start. One of them is about Gauss, Carl Friedrich Gauss, the famous guy. In about 1795, he came up with a method for basically doing what we're going to do in class today in the lab activity. He actually did this not via a lab activity, but rather he used calculus. And I'm going to show you the calculus argument. I'm not going to sort of finish it up. Our book has a nice discussion of that if you'd like. I think the real issue is he found a way for plotting data and plotting a straight line, a least squares line through the data. The reason we call it regression, though, is about 100 years later, this guy named Francis Galton, Charles Darwin's cousin, had data on heights of moms, heights of fathers in families, and the heights of the kids, and based on whether the kid is F or an M, and the height of dad, height of mom. He came up with a way of trying to essentially say, yes, kids in tall families, well, like mom and dad are both tall. Yeah, they tend to be taller than average, but they're shorter than average than their parents are. And in shorter than average families, if mom and dad are both stumpy people, like 5'2", 5'4". These are data from early 1900s, late 1800s. If mom and dad are both really tiny, short people, the kids tend to be short people, but they tend to be taller. Okay. And the method that he named it, he called it regression to mediocrity. We've since sort of changed that up and call it regression to the mean. And so what I want to show you is inside JMP, the data set, and I pulled this down today. It's sort of cool. I got a data set on the data that Galton used. Okay, and you're not going to need this, but if you are interested in looking at it, I will send it to you, or I'll put it in the class website. But basically, he has got data on for families, family one, family two, family three, family four. There's 4 kids in family one and 4 kids in family two. In family three, there's only 2 kids. Yeah. And then we got the height of mom and dad. So dad here, mom right there next door, and the height of kid's height right there. And gender is an M or an F tag. And let's consider the question of just kids that are Fs. So the way I did that is I like highlighted all the M's like this, and I said, let's select all the matching cells. We walked through this in the first lab, and I clicked the hide and exclude button. And so what we're left with is in any data set for the purpose of our analysis and for the purpose of our graph, for the analysis do not use, and hide the data point from the graph or hide the data point in the graph. I've got just the Fs left, kids that are Fs. Okay. And I've plotted here the height of kid against the height of mom. Okay. Height of the daughter, height of the mother. And it looks to me as though there's a bit of a trend. I think you can all maybe see that there's a general upwards trend. Yes? Yay. I didn't even hear any of you unmute and say, hell yeah. But, yeah, we can see a general positive trend. It's pretty weak. When we're talking about correlation yesterday and regression, you'd say, not correlation and scatter plots, you'd say, I'm not really convinced there's a strong trend, but there is definitely a trend. Okay. And so the way Gauss hit on his idea was, well, let's take all the moms that are short. And by short, let's say 5 foot tall or less. And moms that are tall, we'll say 5'7" or taller. So the shorts and the tall moms. And then there's like the mediums, and then the medium shorts and the medium talls. Okay. And again, we suggested this in class yesterday, but if I lump my individual moms into categories, short, medium, medium tall, and then tall, I could find the average value of the mom's height and the average value of the daughter's height in each of these groups. And so in the short moms, the average height is maybe a little bit to the right of that location. But I plotted an average. And in the medium short moms, the average height is close to 62. And then the average of the values for daughter's height is a little bit higher. In the medium heighted moms, the average height there actually, well, let's put the average there. So I'm plotting just the averages in each of these groups. So the average X and the average Y in each of these 1, 2, 3, 4, 5 categories. Literally, Gauss didn't use 5 categories, but you know the story from yesterday. If I connect the dots, like we learned in grade school with the dot to dot things, that looks pretty straight. What we have really here is an idea. If I had a scatter plot, I could draw a straight line through it. Gauss hit on it one way in 1795. Galton hit on it another way in 1896. And since then, we've been using this method called regression to try to describe XY relationships. Let me walk you through how you would do it quickly inside JMP, because you're going to need to do this for the lab. And then we'll talk through a bit more in the way of details. So I'm going to actually, for my own sake, I'm going to choose to analyze the distribution of each mom's height and then the kid's height. Okay, so not the number of kids, but the height of the kids. And these data here, I don't really need the picture, but I freaking got the picture here. Oh, maybe I don't need the picture. Remove the picture. Haha. No, I removed the whole analysis. Darn it. Okay, so let's start over again. Analyze the distribution of my two variables. I recall what I had just done. It will repopulate those guys. And I'm going to want to sort of write down for mom and for the daughter the means and standard deviations. And I'm going to put this in the upper left corner. So for mom, because mom is along the x-axis in my graph, I'm going to write x bar. The average of mom's height is 64.2 or 64.2, yeah, 64.2 inches. And for the daughter's height, it's 64.1 inches on average. Y bar is 64.1 inches. The standard deviation of mom's height is 2.3. I'm clearly doing some rounding here. I probably should do a little bit more precision. SX is, I'm going to go with 2.28. And for the daughter's height, 2.37. And you're sort of thinking, oh, yeah, we could also look at the correlation coefficient. One of the things we walked through with a recent lab is under analyze multivariate. Multivariate, you could just drag mom and the kid's height, mom's height and kid's height, into that. And we see the same scatter plot as before. This lower left one is the one that we had looked at, but the correlation is R is 0.314. R is 0.314. So I'm going to keep those things lying around. So in the context of our graph, and I'm going to recreate it now, under Analyze, fit Y by X, that's the way I'm going to typically choose to do this. Y is what is on the y-axis, of course, the height of the kid. And X is the number along the x-axis, the height of the mother here. And it's all of a sudden on the wrong window, so I drag it over here. So I've got my XY scatter plot, and maybe I'll make this bigger. And I guess all I have to do is to now say, well, fit Y by X seems to do a lot of things. Let's just add in a line. Again, with GMP, you've got this little red triangle thing that says turn some stuff on or off. Make your analysis, your plot, your graph a little bit different, add a line to it. I'm going to draw in that trend line, and I get, well, the equation of a line. We got intercept and then slope. Yeah, literally the height of mom we claim is 43.2 inches, plus then 0.327 times the height of mom. Okay, so how do we get these two numbers here? That's really the question. Okay, I'm going to sort of move this off to the side, and I will bring it back in a little bit. Okay. Sort of getting down to the sort of simple version of this question, I've got data points, which I guess I could have them in a scatter plot. And I'm going to make a very small scatter plot just because it will make my work a little bit easier. If I've got, say, 4 or better yet 3, because that's simpler, different X values and their corresponding Y values, I want to know, well, if I had drawn it in a trend line, and I'm not saying that's the best one, I'm just saying it is a trend line. The trend line itself has errors. How far off are you with this particular trend line to predict Y from X? So any trend line, you go up to the line and then over to get your prediction of the Y value. I guess I could literally say for this is X1, I've got the actual Y1, but I've got my prediction of Y1. I'm going to call that thing Y1 hat. And it's based on, well, you're in X1. We're going to go up and over from the trend line. That's your prediction. And how far off am I? Well, I drew that in pink, but let's now make it yellow because yellow is another fun color. So I'm thinking that's one trend line. I'll call it red. I could have drawn in another trend line, and I'm going to call this stupid. Okay, maybe that's a poor name for a trend line, but the green trend line, is it also a trend line? Yes. Is it also producing predictions of Y? Well, I guess I could read up to the green trend line, and I would say I would bet on Y is there. My Y hat for the green trend line is well above the actual data point. My error here, and let's see if I could get this back. My error with my green trend line is going to be shown in, let's go with blue. So we've got a blue error there, a blue error here, and a blue error there. These 3 errors, well, I don't know. Why would we ever want an error? Yeah, you don't want errors. But are the blue errors bigger in some sense? The first one is about the same size. The second one, maybe I'll circle it. The first one's about the same size. Second one, the blue is a little bit larger. And in the third one, the blue is much, much larger. So I'm thinking red's better than blue. How do we come up with an overall best trend line? We have to define some way of determining what the best is. I'm going to say the following. We're going to say the sum of the squared errors. Aha, sounds like we're going to take those errors, the errors in the trend line, and square them. The sum of the squared errors, which is just a function of A, an intercept, and B, a slope, is equal to summing across all my data points. I goes 1 up to n. My yi, the actual y value, minus a plus b times xi. So indeed, if we have an a, an intercept, and a b, a slope times x, that's going to give me my trend line prediction. So for a given trend line based on a and b, you tell me a and b, I'll tell you this is going to be y hat for that x. And we're going to compare y and y hat, your actual data value, with your trend line estimated or data value. And we're going to take that difference and square it. So we got the sum of the squared errors. And my claim is you want to minimize SSE by choice of the intercept A and B. So we're going to choose A and B to make SS error the smallest possible. The lab activity, the first part asks you to basically choose some A's and B's, intercepts and slopes, and try it out. And you're going to say, well, we tried this one, it was sort of good. We tried that one, it was sort of bad. And you're going to learn how to maybe do the adjustment. What Gauss did 231 years ago. Geez, that's a while. 231 years ago, Gauss basically said, oh, I know how to minimize quadratics. This is something that's quadratic. It's a quadratic in form. We have A and B are both inside the quadratic, and ultimately, things that are quadratics are easy to solve. Okay, so what I'm going to sort of say, and maybe I'll eliminate my graph here because I can, and then I can finish up the math in a conceptual way. What we want to do is take a partial derivative of, darn it, we want to take a partial derivative of SSE, which is based on A and B. With respect to A, set that equal to 0. Take the partial derivative of SSE, which again is a function of both A and B, and say relative to B, also set that to 0. So we're finding the place where, in theory, we should have something maximized or minimized. Because this is a quadratic, I'm thinking the smallest value for SSE could be 0, or it could be larger than 0. And the further the data points are away from your fit, if the y's are not close to where you would predict they would be, SS error will be large. And so this is going to be something that's a parabola, sort of like a bowl shape. If we have A and B, A as like right left relative to the screen, and B is towards or away from the screen, we're going to choose the A and B, which will cause us to be at the bottom of the bowl. Now, some of you are sort of saying, well, you should also check the second order condition and verify that you're not at the top. Well, there is no top. There's only a bottom. Okay. And so the math here, check, check, we could do those things. And now I'm going to sort of show you what that is in terms of what we learned yesterday. And I'm going to sort of gloss over all the details, and I apologize for that, but that's a different class. That's Stat 324 that I already told you about. You could take next if you want to take, another stat class. But ultimately, these two equations taken together imply algebraically the following. The best B out there, the best slope, if you will, is going to be the correlation coefficient R times the standard deviation of the y variable over the standard deviation of the x variable. Hey, I've got all those things lying around. I could calculate it. And the intercept A is going to be y bar, the average y, minus B, that slope we just calculated, times then the average of the x values. So here's where I'm going to need a little bit of calculator help because I don't have one lying around in front of me. I'm going to plug in my numbers for R, 0.314, times then standard deviation of y, that's 2.37, divided by the standard deviation of x, that's 2.28. I need to know the value, and I'm going to, while I'm waiting for y'all, 61.1 minus something, times then x bar with 64.2. So what is this unknown value here equal to?
I got 0.326.
I'm good with that. We'll find out. 0.326. Okay, cool. So what if I have 0.326 times then 64.2 subtracted from 61.0? What is that value? That is the unknown missing intercept. Actually, it's not unknown. It's something we will know in a second. It's going to be about like 2/3 of 60 to 65. I don't know, 40 something.
40.17.
40.17. Okay, that's what you got. I'm cool, happy. I'm not going to guarantee that's true. I am going to say, though, I did a little bit of rounding over here. Notice I told you, yeah, SX and SY. I gave you two-digit precision there and there. You know, I could have done a better job, and I'm sorry I didn't. Oh well. I was trying to illustrate the idea. Okay. So with this situation here, what we've got is um, a way of getting an intercept and a slope. JMP gives you that for free. I sort of maybe quickly went by and said 43.15 plus 0.326 times the height of mom. Actually, I said 0.327 times the height of mom. And so I'm going to view the software saying, let's confirm that the approximate calculations you did are pretty reasonable. Y'all good with that so far? I should not ask those questions in Zoom classes where people don't unmute and say, hell yeah. Is that okay?
Hell yeah.
Appreciate it, Jose. So what we have here is a line that goes through the data. The questions that I have now are, is it the right line? Well, we're going to have to actually tackle the question, is a straight line even a reasonable thing? Some curves are, I guess some data sets are even curved. And our book in chapter 3, section 4, and the lab activity today asks you to try with a curve, and you're going to find with a curve that maybe there are some issues, but we're going to suggest a solution in a curved situation. Besides though the intercept and the slope, we should probably come to terms with what we're literally doing with the intercept and slope. How should we interpret these things? Yeah. And so I apologize in a second. I'm gonna do something because I wanted to look and then I need to haha, perfect. And I'm gonna sort of do this again so you can get that back. Okay, cool. I'm just gonna over here on the side. I've got like two desktops full of clutter that are things I wanted to refer to at all times during class, and something I wanted really got covered up. Okay, so if I was doing this work, finding these errors and minimizing them, the vertical errors are minimized. I can't get any smaller than that. Okay. Literally, I drew this trend line in. If you want to, with the trend line, you literally can say under well, the trend line, you click the linear fit and you say, you know what, I'd like to save those errors, the residuals, if you will. So I'm going to sort of show you in the data set. I sort of should have had this over here earlier when showing you. But when I literally clicked the button and said save the residuals, save these things called residuals, it said save this error, the residual, as you will, the residual of height. What does residual even mean? It's what's left over. And so I guess what we have is the idea that for any particular actual height, and let's go with a different color. Let's go with green again. For the actual height of that person, there's what you would have predicted based on the height of mom. Mom is exactly 5 foot tall. You would have predicted about 63 inches tall. But this particular individual was 66 inches, 60, oh, no, 67.5 inches. And so how far off is she from where you would have predicted her height would be based on only the data set, but not knowing her individual height? You would say we're off by about that amount. That is an error. It's residual variability in heights that is not explained by the height of the mother. And so these residuals are measures of the errors. My claim is if you take these residuals and square them up and sum them, it would be smaller than for any other trend line we could have drawn in. So let's talk about how well I did the wrong thing. Let's talk about how well our data are matching. And did I just, okay, there we go. Perfect. Let's talk about how well the data are matching the trend line, or how well the trend line matches the data. In a conceptual sense here, we've got data points, and I'm trying to draw them with a positive trend line. There we go. And if I had drawn in my friendly trend line, my regression line, if you will, the residual here, E, is just the actual value for Y minus A plus B times XI. That's the error that we have. And the question is, what is the standard deviation of these errors? How far off are we? It's nice to know how far off you are. What if I was going to try to draw these errors in individually, these residuals, if you will? What is the typical size of those? That is a number that I will call S sub E. Think about it as the standard deviation of those residuals. Um, hmm. Okay. How do we get the standard error of the residual? Standard deviation of the residual, sometimes called the standard deviation of the regression line. I don't like that term. I like standard deviation of the residuals a little bit. And that's the typical vertical error size, or the size of the typical vertical error. And that is equal to a number that statisticians like to sometimes call RMSE, for root mean square error, which means, well, it's the sum of the squared errors, okay, for the intercept and slope that are the best possible. So the lowest possible SSE, sum of squared errors, over n minus 2. Okay, so back in that other class where we talked about n minus 1 as sort of like a denominator you use to not have biases. Yeah, we divide through by n minus 2 for that reason here. Okay. Um, that is one number, root mean square error. And so if you have a sum of squared errors, you could divide through by n minus 2, and you have the number called root mean square error, or S sub E. Let's show you where you get that inside of JMP's output, because I think I still have that there. Haha, good. Notice over here off the lower left, we have a summary of how well we fit. One of the numbers that we have is root mean square error. Literally, how far off am I? If I'm trying to predict the height of the kid from the height of mom, I'm going to be off by about 2¼ inches on average. Some people I'm going to peg exactly. Some people I'm going to be off by as much as 2 root mean squared errors. Literally, RMSE, if you go up and down 2 of that, should contain about 95% of the actual data values. So let's sort of show you that in the graph that I've got here. Not for the heights of moms and daughters, but if I go up 2 and down 2, plus or minus 2, and I call it S sub E, that should contain the bulk of about 95% of the data values. Okay. There is another number, though, that we like to use to describe the quality of a fit of a trend line. That number is called R squared. And I want to just sort of save this and then move on to the next page because I'm getting this a bit jumbled. R squared is sometimes called the proportion of the variability of Y that is explained by X. PVE, PVE, proportion of variability explained, is a term that I like to use sometimes. So what fraction of the vertical variability in heights of daughters could be considered related to or explained by the heights of the mothers? Literally, R squared is equal to the correlation coefficient R, and we could square that. Hey, we could also just note that R squared is equal to, no, not equal to, approximately equal to. There's a factor of n minus 2 over n minus 1 in here. I don't want to deal with that. 1 minus SE, the vertical variability squared, over the standard deviation of the y, the variability of y. So let's math that one out a little bit. This numerator is what that is the variability in the residuals. The variability in y, I guess SE over SY is the proportion of variability that is not explained by our trend line. SE is errors, SY is the actual data. The relationship is, well, SE over SY. That's the proportion of variability of Y that's not explained. One minus that has got to be the proportion of variability that is explained by our explanatory variable. So, any questions about any of that so far? I'm apologizing for speaking quickly and not really looking to see if you had typed something in chat. And when I speak quickly, it maybe doesn't encourage you to unmute and then jump right in. So, hey, questions right now?
It's back a half step, but how did you get from the area with the partial derivatives of SSE to the B equals and A equals?
I'm going to say that's a great algebraic exercise for office hours if you want to do that. It is not something I'm requiring or even expecting that you would do for the class. However, our book has a hint about that. And B, um, I don't care if you could replicate it. I want you to understand conceptually, if you have this function, the sum of the squared errors, it's a function of both A and then B, the intercept and the slope, and I guess the data. But if we view the data as fixed, it's only A and B that we get to choose. And I could choose an A-B combination that minimizes SS error. So, John, does that answer your question?
Yeah, would you recommend us just memorizing the B and A form or
Basically, yeah.
like dealing with both? Okay, so we can kind of
I wouldn't even say memorize. I'd say have it written down on
understand.
a cheat sheet.
Gotcha.
And there is an alternate equation in our textbook that I think is less helpful from the understanding point of view, but it is more helpful if you're like my grandma and do all these things by hand. I mean, I told you about my grandma, and she, yeah, literally learned the equation for how to do regression by hand. And it involves fun equations, and let me give you those, like the sum of the x's, the sum of the x's squared, the sum of the y's, and the sum of the y's squared, and the sum of x times y. And if you tell me these five numbers plus n, there is a version of the regression equations that could be boiled down to that. Yay! Are we excited about it? Not really. If you were stuck on an island with only a volleyball in your human blood to work with, and you're trying to figure out some relationship between the time between consecutive waves and then the height of the wave, sure, you should use that method. The method that we have with A and B, I think, is a little bit better for understanding. So I think I successfully addressed your concern, John, but you want to rephrase?
Nope, I think that's good. And then the A and the B that you get are just the optimal A and B that returns the
Yeah.
line.
Yep, yep.
Gotcha.
And that's where I wanted to walk you through something to do with the lab so you're set up well for the lab activity when you go down that path. Again, primarily focus on getting, yeah, sure, the lab done by tomorrow at class time, but make sure you focus your time on being ready for the exam on chapters 1 and 2. But inside that least squares lab, one of the data files it refers to is this Bakersfield real estate least squares Excel file. So I'm just going to download it. Come on. And then I'm just going to go ahead and open it. Come on, where are we? And where did it open? Okay, over here. Good. So here is a data set, and I'm showing you maybe I'll make it a little bit bigger. So I'm showing you these homes in Bakersfield, and you have information about X, which is the size of the home in square feet. Okay. Y is the price that home was in 2003 when it sold. So we're talking 23 years ago. This home in Bakersfield, there was 1,092 feet, sold for $95,000. Yeah. If you tell me information about A and B, the intercept and the slope, which I'm terming B0 and B1, B0 and B1, if you tell me the trend line you think is out there should be 50 as the intercept and a slope of 0.75, if you tell me those are the A and the B you want to work with, that will generate for you this gray straight trend line, and the corresponding little dots are, the predicted values from the trend line. And clearly they're in error because not all of the data points blue are right on the perfectly straight gray line. For example, this first one is way below the trend line's prediction. And I'm saying here's the prediction, here's the actual price of a home, here's the prediction error. Yeah, that's the error in prediction from this particular data point. How far off am I? I'm un I'm over predicting by $37,000. I predicted 132. It sold for 95. I was too high. My prediction was too high by 37. So the negative means you're below the trend line. If we take each of these errors and square them up, and down here in this orange circle, it sort of shows you the size of the squared error for that data point. You can see the squared errors. You can get a sense for, well, this is a crappy trend line because it's like going above the bulk of the data. Yeah, your gut feeling tells you make the trend line lower. What if I go with, instead of, hold on, let me look at one thing first. Oh, my sum of my squared errors here is 39,775. And my average error is like negative 28. My trend line is 28 units too high. What if I have a lower trend line and I go with 40 for now? Boom. It sort of changes the line. It's a little bit lower than it used to be. My first error was like 36.9 negative. Now it's 29.6. It's lower. My sum of my squared errors is going down. You can see these circles in blue are, I'm sorry, circles in orange are a little bit smaller, excepting that one, which was sort of like higher, much higher than the trend line. Now the trend line's gone down. The bulk of the data points are fitting better. Smaller circles. The sum of the squared errors is like 28,000, and my average error is only negative 18. So clearly better. Your job in part of the lab is to try various different intercept slope combinations and see how you can move slowly and haltingly towards the best one. And then it's going to sort of say, okay, now use regression and tell me the intercept and slope and plug it in and verify that it's smaller than anything else that you got. But because you hadn't seen the Excel file before and because it's dorky and I wrote it myself, I thought it's just better to explain it than expect that you're going to know how to read the graph. And what the hell are these orange circles? Well, there's the squared errors, and then we're going to add them up, and there's the sum of squared error. That's our objective function that we want to minimize. Okay, so that's it from my point of view. I'm going to hang for 5 minutes. If you got questions, don't hesitate to ask. Otherwise, I'm stopping the share, and I'm turning off the recording, and I'll wave goodbye.
I was having some questions with using the JMP scatter plots because I'm
Oh,
getting
yeah.
some. Is that something I could get help with?
Yeah, absolutely. And I'll
So,
do that in the context of the data set that we were looking at earlier.
okay. Well,
If you need me to show you something, I'll use that data set. Yeah. So what's
I was
your question?
actually my issue was from problem 4 in chapter 3.1 of the homework with the oil added, oil recovered.
Yeah, yeah.
Uh, what I'm getting is not a proper scatter plot. I'm having like buckets on the right on the y-axis, and I can't figure out how to remove them.
Okay, so I'm just going to show you what I am doing, and I hope it matches your question, but we'll find out. I'm just going to go graph scatter plot or graph builder, I apologize. And all I'm going to do is just grab y, which is the height of the kid, drag it over here. Height of mom, drag it over here. And that's all I'm going to do. I'm even going to turn that off. So that's all I have to do in general. Now, you were referring to question which? Four?
This was 4 in chapter 3.1. I did just drag them in, but I can start over. I can see the screen, by the way.
Okay,
Yeah.
well,
Yeah.
let's see what the question asks first.
This is for part C.
Okay, so oil added, oil recovered. Did you open up the data set that the book has?
Yep, I have it opened.
So why don't I then make sure that you could do the share screen thing, because that will be helpful. So you should be able to either, well, I'm going to sort
Uh,
of, okay, so share settings, I don't know.
I can just send a request.
Yes, that's the way. Like two semi versions of Zoom ago, like the point this, it sort of stopped behaving the way I was used to seeing. So, okay, cool. Show me what you were doing.
So I was dragging in added oil, and then I created one called recovery ratio, which is just recovered oil divided by added oil.
Sure.
Drag that in here. And I
Well, no,
created
don't do that. Don't do that.
oh,
Put it on the X axis.
so recovery ratio on the x-axis.
Um, I think so. Yeah, yeah. Well, I mean,
And
I'm not going to tell you which is X, which is Y, because I don't know.
yeah, so
But
I,
if
I
you
was going to do added oil on the x-axis
perfect, okay.
and then recovery ratio on the y-axis. Oh, you just drag it into the
On the
middle?
left Y axis. Yeah.
Okay. I've just been dragging it into here the whole time because that made more sense, but I guess that
Yeah,
doesn't
okay.
work.
So on the very right, it's grouping according to Y. The lowest ones, the medium lowest, the highest. Not really what you need, not what you want.
Okay. So you drag it into the middle, and this would show that there's a correlation, but it's not great.
Um, you know what? I will claim I think there's a correlation, but I would say we don't know that it's a statistically significant trend line just yet. That will be for
Gotcha.
a much later chapter, right before the final.
Okay, so with the language that we know at this point, we would say it there I don't know what we say there's a trend, but it's not exact or
Yeah, I would say there is a trend. Um, Probably if you check the see where it says statistics and you have this little thing fit drawn in down a little bit, and then down a little bit more. Yeah, if you check where it says F test,
oh p-value point zero. Okay, so the p-value is quite low.
yeah, so we're saying, oh, definitely there is a relationship. And
Yes.
so that's where our RMSE today and R squared, they all appear. The equation for the line, you could draw that in, although we don't need to do that until chapter 3, section 3. I just use fit y by x for certain parts of the trend line, the regression building thing. But yeah, you could use graph builder too, it looks like. Yeah, nice.
Okay. What's can you show me the way that you do it just so that I can compare them?
Yeah. It's not dramatically different, but let's do okay. I have to find where I can share. Okay, share, even though someone else is sharing. Sure, go ahead. And I have to update my machine. Okay, cool. What I've got here, I think you're looking at that good. Under I go with a graph builder. Hmm, there we go. Graph builder is one way that I'll do this. And inside graph builder, I just grab height of y, which is height, drag it onto the y-axis, and your x, I'm going to drag it onto the x-axis. I turn that off. I'm good to go.
Okay. How is that different than how I did it?
Not much. Uh,
Okay.
but I will show you another method in a second. Under analyze multivariate,
Oh,
I could
okay.
say mom's height and kid's height. It's going to give me a correlation, also
And then you
gives
could,
me a graph.
okay. And then you could do mother and father and get a multilinear and stuff like that.
Yes, but that will be another class or later in the term. And
Okay.
I usually use analyze fit y by x, literally, because it says, what's your y? Oh, height of the kid. Boom. Height of mom is your x. You get for free, you get, well, the scatter plot, but you could just add that line in and it gives you all the stuff for free that you want
Gotcha.
in chapter 3, section 3.
Sounds good. And what's it called? Are we going to be doing multilinear in this class later on?
Nope. Nope.
Okay.
That would be stat 324 that I mentioned earlier. Are you thinking about a data science minor?
I'm considering just doing the stats minor maybe, but we'll see.
Yeah.
I did a bit of stats in high school. It wasn't my high school didn't do a AP, but it was like its own honor stats thing. So
So the class that follows this one is stat 3520. And this class covers about a third of the content in 3520. So you could enter that class with finding it pretty easy to sort of get there.
gotcha.
So so yeah, 3520 is the next one. I just don't know what you have time for in your schedule because engineers never have any time in their schedule.
Yeah, I'm CS game development, so
Okay.
I gotta see how to fit it in. So I just gotta do the math and like look at all my classes and see what I actually have time for. It's just so different with the semesters.
Yeah. If you're computer engineering, you said?
Computer science and game dev concentration.
Okay, yeah. So, but if a person's doing all the computer science stuff and they're a stat minor, it's about the same as being a data science minor. Maybe not much different at all. So it really wouldn't matter. A slightly different group of classes, working with software that's pre-existing rather than Python is really the way I
Yeah,
view the
I've
difference.
done my high school class did a lot of R, so I'm familiar with that.
Okay, yeah,
Okay,
Can I ask
thanks.
a question on number
sure.
27 for
Yeah,
2.2?
yeah, yeah.
Yeah, I'm just wondering how to solve number 27 for question 2.2
Okay.
for the homework.
I'm getting there right even as we speak. Sorry about that. I and Kiana, right?
Yep.
I could tell by your voice, and I didn't know you were still there, so I started chatting with John. Sorry.
All good. I made sure to interject when I thought it was appropriate.
Okay, so here what we have is question 27, yeah?
Yeah.
Okay, so in section 2, the XY pairs, the first three have the exact same X. Oh, yeah, yeah, yeah. Got it. Okay, so what's your question?
Oh, I think that's
I'm
the
sorry,
wrong
this is
one.
3 point. Yeah, I wanted chapter 2. I apologize.
Thank you. I'm gonna head out.
Yeah, we'll see it. Aha, nice. Okay, good. Oh, yeah, excellent. We sort of touched base on this in class, but not exactly. What about it, though?
Honestly, when it comes to like just the problem like this, I would just kind of get confused and like just understanding if it's meant to be plugged into JMP to solve it or not.
Nope. Nope, nope. This is a do it by hand.
Okay, because I'm just confused on the portion of times will be farther than one standard deviation from the mean value of completion time. I'm just kind of lost on like where to even start on this
Well, yeah,
problem.
you have to figure out what the mean and the standard deviation are here.
Yeah.
So I'm going to sort of do this the way that I would if I were having only paper and pencil to work with, right?
Yeah.
And it says I've got a distribution here that goes between A and B. All of those values are equally likely. And then anything below A or above B, it's just never going to happen. So that's a uniform distribution. And I guess we know f of x is 1 over b minus a for x is in the range A up to B and 0 pretty much everywhere else otherwise. So far, so good.
Yeah.
One thing in class that we did do is we found that the mean, the average, if you will, is A plus B over 2. And I'm going to sort of say, oh, yeah, that makes sense. Because if you were using a fulcrum here and saying, where would this rectangle balance? It's going to balance right in the middle. So far, so good.
Yeah, so the mu is the median in this case for the
Mu is the median and the mean. Mu is the symbol
okay.
for the mean, but in this case, it happens to also equal the median. Now, our book is nice to tell us that sigma itself is um actually I'm going to go with the book says sigma squared is b minus a squared over 12. I'm going to say that sigma is b minus a, which is like the width over then 2 root 3. Yeah, literally the root of 12 is the root of 3 times 4, and so it's 2 root 3. So
Hmm.
that's my standard deviation. And I guess if I plug in A and B, and shoot, A and B are 4 and 6. So the average is going to be at 5. And in this case, we'd have 6 minus 4 over 2 root 3. And shoot, that's a 1 over root 3. So that's going to give me sort of a mean and a standard deviation, yes?
Yes.
And so I guess I could find plus or minus 1 standard deviation away from the mean, plus or minus 2 standard deviations away from the mean. But root 3, what is that? 1.6?
Let's see.
Yeah, actually 1 over root 3. That's what I want. If you,
1 over root 3.
yeah.
That is, oh my God, so unhelpful. It said it's root 3 over 3. Hold on. To Desmos.
Yeah.
0.577.
So I'm going to call that 0.577. So if I'm right here at the mean of 5 and going
Mm-hmm.
up 5.7, 0.57 units, that's going to be 5.57. And down 1 standard deviation is 4.43. And so it's just find the area between 4.43 and 5.57. That's what you're being asked to do.
Oh, okay.
So this problem has some overhead. The overhead is, okay, here's the mean, here's the standard deviation, here's a number that will get you numerically 5 and then 0.57. By the way, I'd recommend being a little bit more precise than 0.57. Maybe an extra 2 digits of precision would be really nice.
Okay.
And then within 1 standard deviation of the mean, well, shoot, we could find the area of that rectangle. And if we go up and down 2 standard deviations of the mean, it's going to be outside the distribution entirely. So that's a 100% or 1.0 is that area.
All right. So it'd basically be 1 equals and then the difference of 5.57 minus 4.43 or 4.4, yeah, and then like the variable of like the height.
Yeah, which is just, 1 over 2. But
How
I'm
can
going to
it be 1
eyeball
over 2?
this. I'm going to eyeball this and say it's about 0.57. That's my guess. I could be wrong. Maybe it's a little bit more. No, 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 it's more than that. 1.14 over 2. Oh no, yeah, yeah, that's 0.57.
All right. So let's see. I am getting 0.877
Could be
for
right.
the proportion.
Could be right.
All right.
I do not doubt you.
Yeah, because what we're basically solving for with because all of it's equal to 1, because that's what the area has to be.
Yep, yep.
And so it's just equal to them being subtracted, and then finding the height is what we're trying to do for the portion.
Yeah, exactly.
Okay, thank you. Uh, well, that was the main question I had. Thank you very much.
Cool. We'll talk soon.
Yep.
Bye-bye.
See ya.